Welcome to another RDWorks Learning Lab. It's been quite a few weeks now since I started this series off about lenses. The main reason is that I've opened Pandora's box. I really did not know some of the things that I was going to find when I started really looking into how lenses work. Now, my practical experiments are telling me that a lot of the stuff that I'm reading in books is probably correct under certain circumstances. But to be fair, most of those circumstances don't apply to us. I think some of that controversial statement will become clear as I start showing you some of the results that I've been getting. Now that's the reason why it's taken so long for this next video to come along. I've been doing a lot of background work mapping lenses. Now, at the end of the last session, we did a few quick maps of some lenses. These were density maps, energy density maps, to try and work out what's going on inside the lens itself to the energy density. Today, I'm afraid, is going to be a rather heavy session with regard to figures, comparisons of some of the results that I've got. But before I dive into that and discuss those, what I'm going to do is to quickly show you the method by which I'm doing this work. That way, if you want to replicate it, you can do so for yourself. Okay, now here on the edge of my table, I've rigged up a very crude measuring system for the height of my table. Because measuring every height setting with one of these gauges, to be honest, it's a serious pain. And if I set this to 0, like that, 002, and I put my thin piece of card, and I've put it over a hole here, so that when I burn through with my tests, I don't have anything underneath. And then I'm setting the focal distance of this lens with my little dot test to try and get the correct dynamic focal distance. I set my dial indicator here to 0. Okay, now I can drop the table down by 20 millimeters below the focal point, 19.993. So I have a small piece of my thin test card here, which is 0.3 of a millimeter thick, and it's a nice soft card, which is the standard card that I've used throughout these tests. It's thin, and I'll explain the reason for thin as well shortly. 2.5 inch meniscus PVD lens in here, set 20 millimeters below the focal point. So now I'm going to give this a 20 millisecond pulse of energy at 70%. Now 70% power on this machine is about 60 watts coming through the lens and hitting the material. And you will see one or two interesting things happening. Did you see that big sheet of flame that came up in the air? Where did that come from? Okay, so now what I do is to raise the table to the next dimension from 20 millimeters. I'm going to come up to 16 millimeters. Move the head along by 5 millimeters and do another. Move the table up to 10 millimeters. Move the head along 6 millimeters. As we get closer to the focal point, I'm taking more samples. Move the head along, pulse. Move the head along, 4, pulse. Move the head along, pulse. Move the head along. And this theoretically is the focal point. Pulse. And then we'll move backwards by 10 millimeters. And we'll start coming above the focal point now. 2 millimeters above the focal point. 16 and 20. There's my test. And now what I have to do is examine those underneath the microscope. If we look on the back of the card,
we shall see that there are holes punched right through. But if we look on the front of the card, we can hardly see the holes, because round each hole there is a burn mark, a scorch mark, which represents the low energy part of the beam scorching the paper and not destroying the paper and burning its way through. That's basically the test that I've done for each lens. Now, the test itself doesn't take very long. The thing that takes the time is the measurement and then the conversion of those measurements into a graphical format that you can understand. And that's taken me a long time to do that over the past few weeks. Now, I think it's absolutely essential that I have all this information about lenses before I start to analyse why and how different lenses on the same material cut with different parameters. The other thing that we shall try and look at as well is why the same lens cuts different materials with different parameters. Well, here we are sitting comfortably, ready to bore you to tears. I've got to explain what density maps are and how you must read them. And there are lots of other peripheral details that you need to understand. So grab yourself a cup of black coffee or something that's going to keep you awake. That does not include wine or beer. And we'll get started. Now, this little chart here explains why I've been away for a few weeks. Here is a summary of my lens collection. 1.5 inch, 2 inch, 2.5 inch and 4 inch lenses. And what I've been doing, I've been mapping zinc selenide, PVD, zinc selenide, CVD and gallium arsenide lenses. Now, the PVD are the Chinese made brown lenses, and the zinc selenide CVD are the usually USA manufactured lenses by a different process. So we're trying to compare and find out the performance between all these different materials that they use for lenses, of which there are really only 2 that we can use, and the different focal lengths. Now, we're also testing at the same time 2 different shapes. We've got meniscus lenses and we've got plano convex lenses. So, for example, here I've been testing a 38.1 or 1.5 inch lens with the flat face down. I've also tested it with the flat face up. And then I've used an 1.5 inch meniscus lens with the flat face down, or if you like, the concave face down and the concave face up. So that's what this table basically shows me. All the possible combinations and options of lenses that I can use and have used. And in total on here, I've got 54 maps that I've produced. In total, I've probably produced more like 65 or even 70 maps, because some of these I have done twice to make sure that I have repeatability, or possibly I have 2 or 3 lenses which I've been able to test to prove that I've got consistency between lenses. Now, after we've done the burn test that you've just witnessed me doing, each one of these maps takes probably as much as an hour to measure each result and then to plot it and draw it up into a form that you can understand. And here we've just got an example of one of those tests. What I didn't tell you was, when I looked at this, I've done 2 sets of tests. I've done a minimum power test at 36 watts and I've done a maximum power test at 62 watts, so that I can see if there's any difference between the shape of the energy density as I increase the power. This takes 3 or 4 hours to produce this picture here, which shows all the 4 combinations for a given lens. We've got flat face down, down, flat face up, up, and we've got low power, high power, low power, high power. So we've got all the combinations there on one sheet of paper, and they're all scaled exactly the same so that you can see the relative difference. Now, your first observation may well be, hang about, why are these funny shaped curved lines? Well, partly because obviously there's a certain amount of measurement discrepancy, although, as I said, I have been round and I've checked these 2 or 3 times with some lenses to make sure that I've got repeatability, and the shape comes out the same each time. I haven't put any smoothing on these curves, these are just plots of what I've measured. These pieces here, the shaded pieces, are not the beam. It's part of the beam. Let me explain. We know that light travels in straight lines, therefore we cannot have a curved shape. And technically what I've drawn here with these crosses, I suppose, are the beam itself. Because remember, the beam starts off at very large diameter, something like about 12 millimeters diameter for my particular lens system, and then it reduces right the way down to this theoretical zero crossover point, which is the focus point. The spot size happens in this area at the point where the beam is at its minimum width. You can go and look on several places around WWW and you'll find this in optical companies and various other places where they will tell you the nominal spot size for a given type of lens. Here are 3 particular lenses, for example. So the spot size for a 2.5 inch lens would be somewhere in the region of about 0.12. With these maps here, you can see in the background what I've got is the smallest possible dimension that I could find for my hole, and the smallest possible dimension that I could find for the burn associated with that hole. In other words, that's the hole and that's the scorch mark around the outside of the hole. So here we are, the hole and the scorch mark around the outside of the hole. Now the scorch mark is not the same as the beam. The beam is bigger than the scorch mark because the energy density to produce a scorch is a lot more than is available at the outside part of the beam. The beam itself has got a normal distribution energy density, where the energy is highest in the middle of the beam and lowest on the outside part of the beam. And it's very important that you understand this principle of energy density. You'll see that that light is very bright in the middle and it fades away to the outside. Well, that's exactly what that indicates there. We've got a bright light in the middle of the beam and it fades away to nothing on the outside. So that's where the maximum light density or energy density is in the beam. And the higher the energy density, the more damage we can do to the material. Now in mathematical terms, this is a round beam, so we've got basically a funny shaped cone here, like a hill, if it's in 3D. Okay, now the volume underneath that hill there is representative of, in this particular instance, 20% power, which is 30 watts, 32 watts I think it is, something like that. But as we start going towards the focal point, the beam starts compressing its dimension. And as it closes in, we've got still 32 watts of power that's being squashed more and more into this same area. And so at this point here, we've still got a normal distribution curve, but that normal distribution curve now looks like this. Because the area underneath that distribution curve there has got to be equal to the same area as it was there, because we've still got 30 watts that's being compressed down into an incredibly small area. And so as we increase 30 watts down into a smaller and smaller area, the energy density increases. And that's the whole aim of the focal point. We're trying to squash the energy down so that it automatically becomes very, very highly dangerous and able to do a lot of damage. Now this is a map for a plano convex lens. And let's take you back a few sessions. And we talked about plano convex lenses and meniscus lenses when we were trying to hunt for the smallest possible dot. The beams that come in from the outside cross over at a point which is shorter than the focal point. And the beams that cross over from close to the centre of the lens cross over at a point which is further beyond the focal point. So with this type of lens, a plano convex lens, we get this term that I've used, fuzzy focus point, because it's not clearly defined. And if we take a look here, you'll see that what we've got is a shape which looks like that. Okay? Now the lines are crossing over, but they cross over in a strange pattern that produces this outline that looks like this. And you can see here, we're getting closer to that sort of shape here. Our Chinese lenses, they are manufactured with that shape there as part of a sphere. And that's the reason why we get this thing called spherical aberration, which is this uneven, fuzzy focus point. The way that you can fairly cheaply correct for it is to put another spherical shape on the underneath of the lens. And that causes a refocusing, and it helps to reduce the fuzziness down. It doesn't get rid of it completely, it just reduces it to something much more manageable. I'm afraid these are the only two lenses that we have to play with. If you go to an industrial machine, I'm afraid they spend several £100 on a lens as opposed to maybe £10 or £12 as we're spending for these types of lenses. So here's the cheap way of correcting this thing called spherical aberration, which is this effect here. There is another way that you can correct for it, and that's the expensive industrial way, which doesn't look to be any different here, but you'll notice we've got the same pattern of events. We've got a bit of a fuzzy focus here, and it's almost probably virtually perfect there, because this particular lens has been very carefully designed to deal with the wavelength of light that's passing through the lens and correcting it to make sure all the rays do pass through the centre. And that's been corrected by special geometry on the surface of the lens. Here's what we've got, and here's something called an aspheric lens, which is a very funny shaped lens like that, which gives you this almost virtually perfect focus point. But you pay a lot of money for that. You can't buy them as a consumer commodity like we buy our lenses. So I'm afraid we're stuck with these two lens types as the only choice that we can put on our machine. Now they work, but what I'm just about to show you is they don't work to any of the numbers and specifications that you'll find in any theoretical literature associated with lenses. These are very much what I would like to call a compromise lens. Now I didn't realise this until I started doing all this work. There are some really strange properties associated with our lenses, I'm going to call them from now on. The first thing we're going to have to ignore is theoretical spot size. These numbers mean absolutely nothing. I've relied on these numbers for 2 years now, believing that our lenses were half-decent lenses. They work, the same as the Chinese laser machine works. We're getting extremely good value for money, and we're able to perform miracles with something which is only maybe a 95% machine, using maybe 90% technology. It's very important that you understand the basics behind the test that I'm doing. This is not a complete map of lens energy density. It is a picture into the way in which the lens performs using a fixed set of parameters. I tested at 20% and 70% power. They were the two test conditions, roughly equivalent to 36 and 62 watts, approximately twice as much power. Now, the pulse length that I used was 20 milliseconds, and I'll come on to that in a second. And then you saw me use the dot test to fix the focus point for each lens. And then we used a standard set of distances from the focus point to carry out the tests. Now all the tests were carried out with the same material, this 200 gram per square metre test card. First of all, the card has got a destruction threshold where it will burn right the way through. It is a very, very thin card, and basically what it allows us to do is to put the card at various points in the beam and see what damage it can sustain. Now, that's basically sampling the beam at all these different points, and then that allows me to reconstruct from the dimensions of the damage what's happening to the beam itself. Now, as I said, remember that this hatch section here is the scorch mark, the biggest scorch mark that I could find. Now, there are graded scorch marks in that close to the hole it may be dark, and yet furthest away from the hole it'll just be a light scorch. Well, that's what this is. This is the light scorch boundary, or as we get closer to the focus point, we don't get a light scorch, we only get a dark scorch. But it's the scorch boundary. Now, that isn't the same as the shape of the beam, as I just explained to you. The beam light travels more or less in straight lines. So you'll see these funny shapes on here. These are energy density maps. There's two levels on here. We've got the hole, which is burnt through the card, which is this white section here, and the scorch mark, which is round the outside. What I can't do is tell you where the beam is, because I've got no way of measuring where the beam is, because it drops off to almost zero, but it's somewhere out here. Now, in principle, a spot size, regardless of what size it actually is the smallest point where the beams cross over, and you would expect the spot size to be constant. It might not be what the theory says, i.e. for an 1.5" lens, that should be 0.075, around about 3/1000ths of an inch. Well, I don't think we're going to get anywhere near 0.075 millimetres. Okay, now here we've got a 2-inch plano convex lens where we're led to believe that the theoretical spot size will be somewhere in the region of about 0.1 of a millimetre. Well, with low power, we've got 0.2. That's the hole. That's not the spot size, because around the outside of that 0.2 hole, we have got a scorch which goes out to 0.5. But that's not the whole story, because outside the scorched area, we've still got the beam. And the beam comes down here, and let's assume that let's assume for a minute that the beam takes us out to maybe 0.6 or 0.7. Let's just say 0.6 for the sake of argument. So we've actually got a spot size of 0.6, where all the energy of the beam is passing through that 0.6 diameter. Now, we're going to increase the power, but we're not going to change the size of the beam. The beam is going to remain exactly the same size. But what has happened is, as we change the power and we go doubling the power up to 70%, we've gone from 0.2 to 0.3 with our hole, so we've got a 50% increase in the hole diameter. But in addition to that, look, we've moved from 0.5 plus 0.1, which is 0.6, to 0.6 up to 0.7 now. So as the power has increased, so our spot size has increased. Now, this is not a unique phenomenon just here on these two. This is a phenomenon that I've seen on all these maps. The one beside it, for example, at 20% with the lens upside down. We started off with a 0.2 and a 0.4. 0.4 being the scorch mark, which we add another 0.12 just to allow for the beam. But now it's gone from 0.5 up to 0.8 when we double the power. And the hole has doubled in size as well, from 0.2 to 0.4. So the spot size appears to be a variable device. it's about as elastic as the focal point that we found, the dynamic focal point. Obviously the lens is having an effect on the actual energy density itself, because when we turn the lens upside down, look at the difference in the pattern of energy density inside the lens. We can only get 10, 20 millimeters above, and we produce a much smaller hole. These are all exactly the same scale, by the way, so you can see clearly the energy is more densely compacted, but for some reason or other it's not there, because you would expect that because this is a smaller hole and this is a much bigger hole, that this would go right out to the top there. It's puzzling, but it is what it is. It's an energy density map, right? This shows us the degree of damage to the product here and here, and it shows that they're not the same passing through the lens if you turn the lens round. But we're not really interested in what happens up here. It's just a point of interest. What we really want to know is how this lens operates at its focal point. I think at the moment that's enough talk about the maps themselves. There's a whole series of these maps which I'm probably going to put together as a PDF document and make them available so that you can study them for yourself. But that won't happen until we've completed the whole of this lens saga, because I believe it is going to turn into a saga of many sessions, because we haven't even started to do any cutting tests yet. Now, as I was hunting through some technical brochures, this particular company here, which is Thor Labs, a very creditable optical company, I came across this very interesting picture that made me very, very excited, particularly when I looked at this picture here and I saw a spot size of 21 microns, 0.02 millimeters. Let's just zoom in on that a second and show you what I mean. What they're saying here is, if I put a 4-inch lens, plano convex, first, and then follow it with a 4-inch meniscus lens, second, and shine the beam through it, magic happens and I will get a super fine focus point. Now, I immediately disappeared and got some lenses and thought I'll give that a try, because this will get me even better dots than I've been able to get with my compound lens. But my first reaction was to try cutting with it, and it didn't do very well. And I thought, well, I'd better find out maybe why. So let's have a go at mapping it. So I mapped it, and now I can see why it didn't work. It's not very good at all. I can do better with a single lens. 0.4 is the smallest point that I could find, the smallest hole I could produce, and 0.6. So that's no different to maybe an ordinary 2-inch plano convex lens. So not very impressed. But of course, we mustn't dismiss this as being rubbish, because it's not. First of all, these are probably super duper lenses. And secondly, when I start reading underneath here, it says the combination of a lens, their specification lens, and another lens of theirs yields a 21 micron focus spot at a wavelength of 588 nanometers. Now that's 0.6 of a micron. Our wavelength is 10.6 microns. So bear in mind what I said to you, that light can have, you need to have very carefully designed lenses for various wavelengths. So there's a good reason why this wonderful potential setup didn't work for us with our limited ability lenses. And I've got to keep saying that because we haven't got high quality lenses. We've got commercial quality lenses. So already this work has told me that we've got to rein back our expectations beyond what we see specified in books. And we've got to rely on practical results to find the best lens for the best job. Well, after explaining all about these maps, what use are they going to be? Well, when we come to test materials, hopefully we should be able to relate the performance of these density pictures to the effectiveness of cutting certain types of material at certain speeds maybe. We're trying to find out which is the best lens, whether it's flat side down, flat side up, for cutting materials. We'll start off with a few basic materials and we'll try and establish how they cut. And then, having established the best possible lens, we're going to explore another interesting subject, which is why does that lens cut different materials with different parameters? What is it about the material that causes it to require different parameters for cutting? Now, all this energy density stuff that we've been talking about is garage science. You know, all we've got is some very basic information here, but hopefully it's enough to help us answer some questions. Now, if I want to spend a few tens of thousands of pounds, then I suppose I could go out and buy something like this, which analyses the laser beam and tells us exactly to the nth watt how much energy density there is in the beam. It produces a 3D profile, as you can see. Will it tell us how effectively a beam cuts? I can't really say, because this is not measuring the lens, this is actually measuring the laser beam. So it really doesn't do a great deal for us. What we really want to know is how effective our lens, which is the last link in the chain, is at doing the job that we want it to do, which is to cut material. Okay, let's close this session by just finishing off a few loose ends. We started off by talking about this thing called pulse length, which I set to 20 millimeters a second. And I said I'd come back and explain why I chose 20 millisecond pulse length. I know that I can drive a 20 millisecond pulse. It will pierce a nice clean hole through that starts off at around about 0.35, something like that, millimeters, and comes out the other side at around about 0.3. There's a small change in diameter. I started off using that as the basis of my argument. Typically we can expect a dot or a hole of around about a beam width of around about 0.2. That's the best that we could expect from the work that I've done. If we put those holes side by side, we should get 5 holes per millimetre. There's a sort of a perforated cut, if you like. And then we say, well, for most materials, we're going to be cutting in the region of anything between maybe 5, 15 or 20 millimetres a second. But typically, we would expect 10 millimetres a second to cut most materials. So I've chosen 10 millimetres per second as a cut speed. Therefore, in 1 second, 10 millimetres of travel is equivalent to 50 dots, 5 times 10 millimetres. So I've got 50 dots per second. And if I can punch a hole through birch plywood cleanly, then let's assume that I'm going to use my 70%, and in 1 second, if I divide that by 50, it's going to take 0.020 seconds for a dot, or 20 milliseconds. So that is why I chose 20 milliseconds for a pulse length. Okay, now that gave me pretty reasonable results on my card. Well, here is a 2-inch meniscus PVD lens, and used the wrong way up, here are the 2 maps, low power and high power, but using a 20 millisecond pulse. So we've got a certain amount of energy in every pulse that we fire at our piece of card. There's a fixed amount of energy. It doesn't sustain itself and burn a bigger and bigger hole. It's just enough energy in there to burn that particular size hole. So I did experiment with a pulse length of 50 milliseconds. So there's 2.5 times the power in here than we've got there. With this low power map, we've got 0.5 plus maybe 0.1, so we may have a 0.6 neck across there. We've got 0.7 here, plus maybe another 0.1 or 2, I don't know. But so the same rules apply. The more power we try and push through the lens, the bigger the spot size. And the other interesting thing about this particular map is, although we've got 2.5 times as much power here, I would have expected this to creep up here more because we've got more energy going up the beam, but it doesn't appear to be the case. What seems to be happening is the energy is spreading out inside the beam more so that we get only to the same depth. There's the same amount of potential burning capability here on this smaller diameter, and on this bigger diameter we might have more power, but that's as far as we can stretch up. So we're not improving our range, if you like, of burnability just because we increase the power of the pulse. So that's the reason why I decided to stick with just an ordinary 20 millisecond pulse. It keeps the pictures compact and it doesn't detract from the information that we're getting. Long way to go. On that note, go and finish your coffee. Now you can have that drink of wine or beer, and I'll see you in the next session.